Hello everyone, my name is Deck and the title of my presentation today is Fabrication of Flexible and Transferable Resistant Temperature Detectors RTDs via Fused Deposition Modeling 3D Printing. I will just start with a brief introduction about myself and my research interest. I am a PhD student at the University of Sussex from the year 2017 to 2021. I am currently very near to the completion of my PhD. I am in the School of Chemistry, but I mainly worked in the Pharmaceutics Research Lab and the Flexible Electronics Lab. My research interest lies in using cost-effective 3D printing techniques for pharmaceutical and biomedical applications. For example, one aspect of my work would be looking into fabrication of customizable drug delivery system using 3D printing. The drug delivery systems were customized in terms of its drug release patterns, and this was done by preparing 3D printable filaments using various pharmaceutical polymers. I'm also interested in the fabrication of flexible sensors for biomedical applications using 3D printing. This is because the 3D printing technique is an automated one, which could help reduce the need for manual handling, and the possibility of 3D printing flexible sensors can be integrated with the printing process of drug delivery systems, where this integrated system can potentially be used to form a smart drug delivery device. The motivation of my presentation today is from the interest in using a fused deposition modeling, which is FDM 3D printing for biomedical applications. This will be the focus on using FDM for fabrication of flexible temperature sensors, which may be suitable for biomedical application. Despite temperature being one of the most common and simple parameters that is measured in biomedical applications, it is still a very important one, particularly for medical diagnosis. Due to the irregularity of our human body surface, a flexible temperature sensor may be highly desirable so that it can conform to these irregular surfaces. I will now briefly explain the mechanism of a FDM 3D printer. FDM 3D printer can be considered the most cost-effective and easily accessible 3D printer amongst all the commercially available 3D printers. The main printing materials of FDM 3D printers are typically thermoplastic filaments. These filaments are melted at high temperatures through the printing nozzle head of the printer, then extruded onto a printing platform. Once the melted plastics were extruded, they will solidify as they cool down and they form a solid object. This will be the printing technique of the FDM, and where the 3D object would be built layer upon layers of the extruded molten filaments. 3D printing was mainly a rapid prototyping method, but nowadays various industries have been using it for production as well. Here, I will speak briefly on how 3D printing have been used for electronic applications. One of the first electronic components that have been 3D printed are the printed circuit boards, PCBs. Although not specific to FDM 3D printing, but other 3D printing techniques have been used to produce PCBs, where these PCBs have been used in most electronic devices today, such as smartphones, televisions, computers, medical equipment, and also many other consumer electronics. Apart from that, 3D printing has been used to produce personalized wearable devices such as smartwatches, smart textiles, and also some more other examples where 3D printing has been used, including electronic components such as antennas, batteries, as well as electronic components for wireless communications. The advantages of using 3D printing is that it is very effective in producing complex geometries, and some advanced 3D printers are even capable of printing on non-planar or non-flat surfaces. This would offer great flexibility in design of the product, which was often constrained when traditional manufacturing techniques were used. There is also less waste with 3D printing, as only what is needed is printed. Also, the limitation of 3D printing in terms of electronic application would be that there are limited 3D printing materials that can be used for electronic applications. Now, one of the works that I have done using FDM 3D printer is to print simple and flexible RTDs. This is a very low cost method to produce some quick temperature sensors. So two types of commercially available conductive polylactic acid PLA filaments were used as the printing material. One contained the carbon black and the other contained graphene. These sensors were printed on flexible mylar substrate, and the printing temperatures were shown here, where the printing temperature was set at 225 degrees Celsius and the print bed temperature was set at 70 degrees Celsius to allow a slower cooling of the extruded filament. Each layer height was set at 0.1 millimeters and 3 total layers were printed. The image on the left here is the CAD model of the RTD used for printing, and the images on the right are the printed RTDs, where we can see that the printed structures may not be perfectly straight. This is mainly due to the poor resolution of the printing technique. Next, to measure the temperature sensing ability of the 3D printed sensors, the sensors were placed on a hot plate where the temperature was increased from 15 degrees Celsius to 80 degrees Celsius with a 5 degrees Celsius increment at every measuring point, and the resistance of the 3D printed RTDs were measured. The results were shown here, and the 3D printed sensors showed positive temperature coefficient, and the sensitivity of the temperature sensors were measured and shown here using the temperature coefficient of the resistance for the sensors. It is shown that the carbon black PLA sensor had a sensitivity of around 0.014 per degree Celsius, whereas the graphene PLA sensor had a sensitivity of around 0.005 per degree Celsius. As shown in the graph, the increase in resistance with temperature for the carbon black PLA sensor was more linear than the graphene PLA sensor. Now, temperature cyclic test was then carried out to the 3D printed sensors to determine the response of the sensors to cyclic temperatures. This is because it is important for a temperature sensor to be able to produce repeatable measurements. The temperature range was set between 20 degrees C to 40 degrees Celsius, and this was chosen as it is within the fluctuation of the skin temperature range. Of course, this depends on the activities of the person at that time. Again, the sensors were placed on a hot plate and the temperature was set to increase from 20 degrees Celsius to 40 degrees Celsius. Then the change in resistance was measured for 5 minutes at every second, and after 5 minutes the plate was cooled down to 20 degrees Celsius. The results showed that the carbon black PLA temperature sensor was more reliable and stable than the graphene PLA sensors. The resistance of the graphene PLA sensor did not return to the value when it was first measured at the end of the cycle, and there were some small fluctuations during the measurements. The change in resistance of the graphene PLA seems to have experienced a lag as the temperature changed, whereas the response of carbon black PLA seems to be quicker than the graphene. Then the 3D printed sensors were peeled from its mylar substrate and transferred to two curved surfaces at different radii. So this shows the transferability and the stability of the sensors when measuring their resistance on curved surfaces. The two curved surfaces have radius of one is 3.5 centimeters and the other is 2.55 centimeters. So the measurements were taken at room temperature for this test. The resistance of the sensors were measured first when they were flat, then also when then they were bent over the curved surface, and this was bent over 5 cycles in total. So as expected, the resistance of the sensors increased as it was bent over curved surfaces. The estimated strain on a smaller radius is larger because larger than the larger radius, of course. Then hence the change in resistance also increased when the sensors were bent over smaller radius curved surface. Nevertheless, the carbon black PLA sensors showed better stability and resistance to bending as change is smaller than the graphene PLA sensor. So in conclusion, for this simple study that uses a low-cost FDM 3D printing to produce flexible RTD sensors, the fabricated flexible RTD sensors showed good stability and temperature response despite the poor resolution, and the conductive materials used, although in the form of polymeric filaments, show excellent conductivity, response, and also sensitivity to the temperature change. Overall, the sensors containing carbon black seem to have better sensitivity and stability than the PLA infused with graphene. The 3D printed sensors also offer the benefit of being transferred to other substrate whilst maintaining its stability. So this is the end of my presentation, and thank you very much for listening.